In this segment, we're going to review acid-base titrations. In a titration, a solution of accurately known concentration is gradually added to another solution of unknown concentration until the chemical reaction between the two solutions is complete. Looking at the photographs, the Erlenmeyer flask contains one of the solutions. The other solutions is in the burette. An indicator is added to determine the equivalence point. That is the point at which the reaction is complete. The indicator changes color at or near the equivalence point. Notice in the photographs that the solution changes from colorless to pink. Strong acid, strong base titrations. An example would be sodium hydroxide and hydrochloric acid. The net ionic equation is the hydroxide ion reacts with the hydrogen ion to form water. Here is a pH titration curve. pH is shown versus the volume of sodium hydroxide added. Since this is a strong acid, strong base titration, the equivalence point occurs at pH of 7. Weak acid, strong base titration. Acetic acid plus sodium hydroxide is the example here. The net ionic equation is that the acetic acid reacts with the hydroxide ion, forming the acetate ion and water. This time the equivalence point will be greater than 7, since the sodium hydroxide is predominant. At the equivalence point, the following equilibrium is established. The acetate ion plus water is in equilibrium with the hydroxide ion and acetic acid. Look at the pH curve this time. The pH at the equivalence point is 8.72. It's higher than 7 because the base predominates. Strong acid, weak base titrations. Hydrochloric acid this time reacts with ammonia to form ammonium chloride. The net ionic equation is hydrogen ion plus ammonia forms ammonium chloride. This time the equivalence point will occur at a pH less than 7 as the strong acid predominates. Ammonium ion plus water will be in equilibrium with ammonia plus hydrogen ion. The titration curve this time starts at a high pH. Since we have ammonia in the Erlenmeyer flask, we add this time hydrochloric acid, so the pH decreases until it reaches the equivalence point of 5.28. Acid-base indicators are all weak acids. They establish an equilibrium between the H indicator, hydrogen ion, and ion minus the anion. The ratio between the concentration of the indicator compared to the concentration of the ion, if it's greater than 10, then HIN predominates, and that's the color. If it's less than 10, the color of the conjugate base predominates. Here are some common acid-base indicators. You can notice the color changes and also the pH range that they indicate. Here's a titration curve of a strong acid with a strong base. Notice that the equivalence point can be determined either with methyl red or phenolphthalein. We're looking for the part of the curve that is almost vertical. Which indicator would you use for titration of HNO2 with potassium hydroxide? It's a weak acid being titrated with a strong base. At the equivalence point, you will have a conjugate base of a weak acid. The equivalence point will be greater than 7. Looking at the table of common acid-base indicators, you can use creosol red or phenolphthalein.